Hi, my name is Peter Matrakos. I'm the Instrument Facility Manager for the core facility instruments. Today we'll actually be producing some instructional videos for the instrumentation that we have here. In particular, we're going to be looking at the ICP-OES today. So this is our ICP-OES. Basically, it's our inductively coupled plasma optical emission spectrometer. It's what we have here at UTM to actually produce, to get elemental analysis on any sample that you might be interested in looking at. We can literally look at dozens of elements simultaneously and possibly even hundreds of emission lines. To begin with, this is the ICP itself. We can open the door here. You can actually take a look at the torch chamber right here. This is basically the unit that actually gets heated up to 6,000 or 7,000 degrees Kelvin and volatilizes the sample, gets it in an elemental form, and we can actually start measuring the different elements. This is the torch, the RF coil, and the optics are all obviously behind the instrument. So we can close this up. And what feeds the system is the spray chamber. So here's where we aerosolize our sample, we introduce it, and it gets drawn into the torch and gets measured. Right beside that, I'll close this up, is our peristaltic pump. So the pump itself will actually draw the solution into the instrument, and it'll also bring it to waste. So down here you can actually see where we have a 2% nitric acid solution that'll get drawn for rinsing. And we also have a drain that'll actually get rid of all the excess waste that's not being actually introduced into the plasma. So this should always be filled before starting a run, and this should be emptied if it's actually starting to get full. This is all connected basically up to our pump and as well as our CTAC auto sampler. It actually contains 4 racks with 60 samples that you can actually place at any point in time. The racks are labeled left to right, 1, 2, 3, and 4 right now, which is over here. We actually use 2 gases to provide the instrument, one being the plasma gas, which is argon, and the other being a purge gas, which actually helps get rid of oxygen in our plasma chamber. Both gases are actually located on the manifold on the wall behind me. They are labeled on the wall. This is our argon tanks, and the nitrogen is on the opposite wall, labeled once again. Generally speaking, we indicate which tank is actually in service with this knob right here, and all you would need to do is simply turn on the gas so that it can feed the instrument. And same thing with the nitrogen as well. You can turn it on from the opposite wall over here. Once again, in this case, it's indicating the one on the right is the one to operate. Simply turn it up and make sure there's actually pressure to the instrument. So now that we've turned on both gases to the instrument, we want to go back to the back of the instrument in order to turn on the gases to the instrument. In this case, we have a final stage control to the argon and the nitrogen, top and bottom. The instrument needs to only have nitrogen flowing in it for about 4 to 8 hours before the instrument is operational. So to do that, simply you just have to turn on the lever, have it pointing down. The argon is quite expensive, so the argon we do not actually use until maybe several minutes before the instrument is operational. Finally, the final device that we have related to the instrument that we need to be aware of, but once again we would not need to turn this on until just before the instrument would be operational, is our chilling unit. So you'll have to go back here several minutes before the instrument's ready to go and hit the on-off switch to get it operational, and it should be fully operational, fully ready to go within a couple of minutes. So now that we've actually finished a quick overview of the ICP-OES, we have a 4 to 8 hour window of opportunity where the nitrogen gas is purging the system. So this is where we're going to spend our time with our method development, and we'll need to work on the software. So now that we're actually at the software, it's the QTegra software that we have available here that communicates with the instrument. So just double click and wait for it to open. So the software has both control over the iCAP OES, the ICP-OES, as well as the auto sampler. They're both indicated over here. And it has direct control over them. They speak to one another, speak to the software, so they can collect the data properly. And when it's all done, it'll also collect all the data and put it into an Excel format that you can actually access at home. Currently, as you can see, there's the purge gas right here. This is the one thing you need to pay attention to before even method development. You want to make sure that your purge gas flow, at a trickle, you're going to wait 8 hours for the instrument to purge. If you want to speed it up a little bit, you can select normal. But in order to apply that, there's a little bit of a trick to it. You have to adjust the pump speed to get this to apply, for that button to come up. So you can put it back down to 0 because you won't need the pump for a while, and then hit apply. And now you should see both the setting and the actual readout at normal. In this case, you should be waiting about 4 hours for purging. If you really wanted to go to a higher speed and do it in a quicker amount of time, although you'd be using a lot more gas, you could put it to high, and that would be simply a 2-hour purge. So at this point, other than doing that and making sure you know how long you'll need to give yourself before the instrument will be ready, here's where we head over to our lab books. So we can actually just click on the left portion of the software here. And what we're going to do is we're going to create a lab book. So best way to do this is simply to call up an old lab book. Doesn't matter which one it is. If it's one in particular that you're aware of, you can just select from the list. In fact, let's just select the one that's currently in the queue here. And what you need to do now is go back up to the name and give it a different name. So let's just call it a test for now. Enter. And we go down back here to this tab and we create our lab book. Now this current method actually has, as you can see, a sample list of 37 samples. You will tailor yours according to what you want to run. So currently we just have 3 samples set up. So what we'll do is we'll select all of them and we will cut those ones. So we're simply going to run a blank. We're going to run a standard sample, and then we're going to run an unknown, which we'll have to designate. Now, before getting to the actual details of this, what we should do is go to the method parameters, double-click on it, and you can see your periodic table here. Currently, this method that was previously used, if you click on this, you'll see that it actually selected 3 zinc lines, the one at 202, 206, and 334 nanometers. And those are the lines that they were interested in looking at. If you're not interested in it, deselect them. And let's say you'd be interested in looking at some heavier metals, like chromium, like manganese, like iron, like nickel, like copper, and zinc. You can select multitudes, or you can even go in, right click, and you can see which lines were actually selected. So the selection is a bit of a trial and error method where you determine what lines work best for you in terms of spectral overlap. If you decide that these lines that you chose originally are good for you, that's fine. That being said, if you do have some spectral overlap, you might want to choose a different line. They are organized in terms of relative intensities, so you have your most intense lines at the top, and if you scroll down, you'll see your least intense lines. Ideally, you'd like to choose something that's really intense so you can improve your signal to noise, but if otherwise, that they have a bit of spectral overlap, you may even want to choose 2, even 3 different lines so that when you look at your data, you can decide whether or not there is some overlap that might interfere with your quantitation. You'll have maybe 3 lines to choose from. And if one or 2 of them work out good for you, ideally you'd want to choose one with a higher relative intensity to improve your overall quantitation. So let's say these are the elements that you want to look at, and these are the lines you wish to choose. You can work your way down. Typically, unless there's a good reason to, I'm just going to measure modes, you can select axial. You'll usually get better signal to noise with an axial mode. It's almost a 10-to-1 improvement to radial. So you can measure your emission lines both axially and radially. Axial will actually give you a better signal to noise, a better quantitation, and a lower limit of detection to work with. Now, we're going to go step by step. We'll go to acquisition parameters. Now, here's where all the lines that you chose will actually be, it'll have both the element as well as the individual lines that you chose. So remember, we chose 3 for chromium. They're all here, and they're displayed. Now, in terms of slit position, that's not a concern that you have to work with. But by default, even though you just selected axial mode, by default the program will actually apply radial mode to each one of those lines. So you have to manually go in and change them to axial. At this point, this is all that you'll need to actually do with the acquisition parameters in order to make sure that your sample will collect as you wish. Generally speaking, intelligent uptake and rinse, it's part of the software, but it's not part of our instrument. Once again, inter-element corrections not important. Standards, they are. So here's where you decide how many calibration standards you need to run. The previous method required 4. We're only going to have 1 in our test method. So we can actually select and delete the ones that we're not interested in. So we'll just keep 1. You can choose as many calibration standards as you wish. So now we have 1 current standard, but as you can see, it's the element that was originally in the method, zinc. But we chose several other elements that we're not going to be, several other elements that we're going to be measuring instead of zinc. Here is where you need to specifically select the ones that you chose. 1 time for each element, basically. And once you've selected them all, here's where you need to know the concentration of the standard that you actually are using so that you can tell the instrument how to apply its number of counts that it collects to concentration. So it can apply that calibration to your samples when you do run them. So here you can actually change the concentration. We're only dealing with, let's say, 100 parts per billion standard for zinc, but 1 ppm for chromium, 10 ppb, and 1. So depending on the actual standard that you've either made or purchased, your concentrations may be quite different for all the different elements that you're looking at, or you can decide to make them all the same concentration. Whatever the case may be, make sure that you actually tell the instrument what the concentration of each of the elements is so it can properly apply the calibration curve to it. Quantification, this should not be an issue at all. We can actually switch from there to ratios. Quality control, once again, not important. When we do quantify our results at the end, we may need to come back to this table, but we may not have to. So at this point, you can see depiction of the auto sampler table. You can see where all the positions are. So left to right, once again, this is position. This is rack 1, rack 2, rack 3, rack 4, and these are all the positions in behind the racks. Okay, you just need to remember those. Right now we have that 4th rack empty. If we wanted to include it, we could always select 60 vials and include it, but we don't wish to. We'll simply leave it as empty. We're not going to deal with a manual sample control. The samples will be introduced into the instrument through the auto sampler. We're going to come back to our sample list, and once again, you can actually create a list of up to 240 samples, including your blank, your standards, and all that, all of that. Should you decide to. For simplicity, we're just going to make these 3 samples. We're going to create a blank, a standard solution right here, and an unknown, which is a sample of interest that you want to measure. So bare minimum that you need to run on the system, you need to have 1 blank, 1 standard solution, and your unknown to actually get a result. Since the instrument has a wide range, a linear range to it, almost 6 orders of magnitude, you can get away with actually just 1 standard. Typically though, you'd probably be producing 2 to 3 samples. But in terms of today. Basically, we just want to have the basic run on the system. At this point, we can actually, where is it? We can save the table. If we've completed our method development, we've chosen the elements that we wish to run, we created our table, we can simply save it, and it's going to be, the instrument's going to be ready to go once the nitrogen is actually purged, the system. We can head over back to the home page and go back to the dashboard. So at this point, you have all of these, you can take a look on this page, you can see all of these interlocks. All of these need to be green in order for us to actually even consider to start the instrument. The plasma gas we have not turned on, obviously it's red. The detector water flow is controlled by the chiller, it's off, it's red. And the detector temperature, once again, the chiller is not working, and so it's red as well. Everything else is ready to go. So once we're ready, once we know we've purged the system, we simply turn on the plasma gas, we turn on the chiller, wait for all of these lights, all of these interlocks to turn green before we actually start the instrument, and the torch should light at that point, and we just simply have to start our sample table at that point, and it'll collect. If by some chance you happen to be, right now we're seeing all the iCAP OES parameters, and these are the most important ones when considering starting the instrument. At this point, we've actually completed our method development, and we simply have to wait for 4 hours in normal mode for purging of the system, and the system is sort of in standby mode at the moment. We'll come back to it after 4 hours, and we'll turn on the chiller, turn on the plasma gas, and the system will be ready to run our samples. So now it's been 4 hours, our system is actually purged. What we've done in the meantime is actually prepare our samples, our blank, our standard, and our unknown in positions 1, 2, 3 that mimic what we had in the software originally. And what we're going to do is put it in position rack number 1, so the instrument knows to collect from that position. And what we'll also do is tie down both of our lines here, one for waste and one for introduction of the sample into the plasma, and tighten it down so that the pump will actually get a good grip on the lines and draw solution through. And then finally, we're going to head in behind the instrument. We want to come over to the back of the instrument, back side of the instrument, and turn on the plasma gas. Counterclockwise rotation. There's no need to adjust the pressure, it's already been regulated. Should just need to turn this on. And finally, we'll head over to the chilling unit so that we can turn it on and wait for the system to cool down before we use the instrument. So now that the chiller and the plasma gas have been both turned on, we come back to the software. We want to make sure that all of our interlocks are fully green, indicating that it's time that we can actually spend to start up our plasma and start the instrument and have it in its standby mode. In order to facilitate that, in this case we can see everything is green. We are going to go over to this Get Ready button, left click, and simply hit OK. System should be getting itself into a ready mode. What we should be waiting for at this moment is hopefully seeing our plasma form in this window right here. It'll be obvious when that's actually happened. You can actually see it in between in there right now. So we want to see the transition from that to seeing our peristaltic pump working and drawing in solution and feeding the spray chamber. And currently the sipper, you can see, is actually drawing solution from the with the 2% nitric acid solution that we have at the bottom there. At this point, the system should be in the ready mode. The peristaltic pump is actually working. We can actually see that there's solution running through into the spray chamber and as well to waste. Make sure that you have enough solution in here so that the system does not run dry at any point in time. So if it's filled, it should be more than enough. So we come back to the software. We select our tab here for the lab book that we actually had created, and basically what we do is we send, at the bottom here we have a scheduler, and it schedules all the different tables, all the different samples that we the different samples that we wish to run. The way to start the whole instrument and run your table is simply to schedule this to the lab book. So left click, we should see the process down here in the scheduler. And at this point, we just simply start the scheduler and we can head over to the instrument. So now we've started our sample list, our lab book, and as you can see, the sipper, the auto sampler, is actually going to the first sample that we put in our sequence, which is our blank, and it's drawing in solution into our plasma. So each sample will take about 2 minutes to collect, and the first 30 seconds will be spent rinsing the line so that you don't have to worry about carryover. When it's done with a sample, it'll go to the standard, and then to your sample in this case, or multitude of samples depending on your particular number of samples that you're going to be looking at. It'll finish the sequence and we'll be ready to actually look at the data. What we want to do is go to the home page, select the auto sampler canvas, call up rack number 4, and select position 26, which should be smack dab in the middle of where the beaker with deionized water actually is resting. So at this point you can see the deionized water, the sipper is actually in the deionized water. We'll simply allow the line to actually rinse itself out for 2 minutes, and then we'll return the sipper back hovering over the 2% nitric acid rinse, and let the line run dry before we actually start the shutdown of the instrument. So at this point I'm simply going to put the sipper back to the home position. And it'll hover over the position, just drawing in air to actually clean the line out so that it's not sitting with 2% nitric acid or a more concentrated solution until the next time you use the instrument. So now you've actually seen all the parts of the ICP-OES. You've seen how to create your methods. You've seen how to start your methods, how to start the equipment, and now what we're going to proceed to is actually properly shutting down the instrument. What we're going to do is put the sipper line from the deionized water to our home position, in which it'll hover over the rinsing solution without actually being in solution. And we'll let the line dry itself out so we don't have nitric acid solution sitting in the line over the week or until the next time the equipment's actually being used. And now we are going to go back to the Get Ready button, left click, and simply shut down the instrument. And at this point, what we like to do is go back to the iCAP OES box, and what we wish to do is turn the torch off, the purge gas, and then turn the chiller off. So now all we simply want to do is turn the knob for the argon gas counterclockwise to make sure that the gas to the instrument is turned off. And here we'll be turning off the instrument by hitting the switch, and we'll wait for it to properly shut down. Once we've turned off the gas directly to the instrument for the argon, we're also going to turn off the gas from the tank. Now we come back to the software and we can take a look at our interlocks and see that our detector water flow and detector temperature are now no longer green. Our plasma gas pressure is still green, but once the gas in the system actually purges itself out of the system, it will turn red. There's no need to wait for that. Finally, the detector itself does require about a 5-minute wait before we turn the nitrogen gas off in order to prevent any moisture building up on the detector, which is normally at about -40 degrees Celsius. So we'll wait 5 minutes, we'll turn off the nitrogen gas, and we should have completed our shutdown procedure. So as we've already done for the plasma gas, we're going to turn the nitrogen gas off as well directly to the instrument by simply pulling the lever horizontal, and we'll head over to the tank and make sure we turn off the gas at the tank. Okay. At this point, you're going to be going back to the software, you're going to save your data, you're going to quit the program, and now you've actually seen both the operation of the instrument, the startup, the shutdown, and if you have any further questions, please feel free to contact me. Thank you.